Hey guys, welcome back to Pop 'em Up Chem. Sorry about the delay on some of the uploads. In this video, we're going to be starting Unit 4/14 of the IB specification, that's structure and bonding, and we're going to start it off with looking at covalent bonding. So what we're going to do is we're going to define covalent bonding, look at how electronegativity can affect covalent bonds, and then we're going to contrast simple and giant covalent structures. Firstly, let's think about bonding in general. So there's kind of two major parts of bonding. There is chemical and physical bonding. So chemical bonding includes covalent bonds, which we're doing in this video, ionic and metallic bonding, which will be coming later in the unit. Physical bonds are intermolecular forces, sometimes called van der Waals forces. These split into three main categories: London forces, which are also called induced dipole, instantaneous dipole, and sometimes called dispersion forces. We also have Debye forces, which are also called induced to permanent dipole forces. And lastly, we have Keeson forces, which are also called dipole-dipole forces or permanent dipole to permanent dipole forces, and can also include hydrogen bonds. For now though, let's bring our attention back to covalent bonding. So how do we define a covalent bond? Well, a covalent bond is the attraction of two atoms to a shared pair of electrons. We can conceptualize this as thinking of two nuclei with outer electrons, and we know they want to complete their outer shell, and so they may place these electrons, for want of a better word, between each other. And what that does is that creates a mutual attraction between the nuclei and the electrons that are located in between the two nuclei. And we can think about this as completing their outer electrons. If we think about here, we've got a 1s orbital, and so that wants two electrons to complete it. So we can think of that as each nuclei adding an electron to its outer shell, and therefore each nuclei having a complete shell when they are paired together in this system, hence why we describe them as shared electrons. Typically, we see this kind of bonding between non-metals. To help us predict these kind of bonds, we can use the octet rule. And what the octet rule states is the atoms usually form bonds based on the octet rule. That is, they want to have 8 electrons in their outer shell. We could also think about this as atoms forming as many bonds as they have gaps in that octet. For example, if they have 7 electrons, they have 1 gap and so can form a single bond. Something in group 5 would have 5 electrons in the outer shell and therefore would have 3 gaps and would have the ability to form 3 bonds. Now, these bonds can organize themselves in different ways. We can have single, double, triple, and even dative bonds. For example, in Cl2, we have 2 atoms with 1 gap, so they form a single bond, which is represented by a line between them, which indicates that they have 2 shared electrons between them, and so is a single covalent bond. In CO2, however, we have oxygen, which has 6 outer electrons, and carbon, which has 4. So carbon can form 4 bonds and oxygen can form 2, which leaves these 2 lines representing double bonds, and that is 4 shared electrons between each of the carbon and oxygen atoms. However, oxygen can also form 2 single bonds. As we said, it has 6 electrons in its outer shell and so has 2 gaps. So it forms 2 bonds, but they could be in a single configuration or in a double bond configuration. As I said before, carbon can have 4 gaps and so make 4 bonds. So here we have carbon bonded to another carbon with 3 lines representing a triple bond or 6 shared electrons, and obviously 1 single bond with hydrogen to form a total of 4 overall bonds. You'll notice that that is congruent with CO2, which we did just above, where the carbon has 2 double bonds either side, still totaling 4 overall bonds. Now, there are cases in which some atoms can contribute both of the overall electrons that are in the covalent bond between the two atoms. This is called a dative or coordinate bond. We can use the example of the nitrogen in ammonia. Remember, nitrogen has 5 outer electrons, and so in NH3 it forms 3 single bonds, gives 1 electron to each of those, and then has a lone pair all to itself. And what this lone pair can do is it can find a H+, and it can actually donate both of the electrons to a bond between the nitrogen and the hydrogen, and this forms NH4+, which is the ammonium ion, and we represent that with a arrow going towards the hydrogen atom from the nitrogen. Now, it is important to mention that these 2 bonds are identical once they are formed. They have the same bond enthalpy, they have the same length, they have the same strength. So they are not different once they are formed, it's only the formation that is different. And then we put some square brackets around it with a plus to indicate that this is an ion and has a charge. Now, the bonds get stronger as we go from single, double to triple bonds, so we get an increasing bond strength. However, we get the opposite when we look at the length. We get a decreasing bond length as we go from single, double to triple. Now, just looking in a little bit more detail at coordinate or dative bonding, as I mentioned, of course, the dative bond differs only in its formation. The rest of the bond is the same. We can also say to watch out, donor species will always have a spare pair of electrons, and acceptor species will always have an incomplete octet. Looking back to our formation of ammonium ion example, we can see that the NH3 before bonding has a spare pair of electrons, so it is the donor, and the acceptor is H+, which has an incomplete 1s orbital. So the nitrogen can donate both electrons and form that dative bond. So, like any good rule, there are indeed exceptions to the octet rule. Now, carbon, nitrogen, oxygen, and fluorine always obey the rule, and these make up a certain majority of compounds, so that's good. But there are 2 types of exceptions. Firstly, we'll look at reduced octet exceptions. These are atoms that will happily be stable with less than 8. Now, the first most obvious one is hydrogen, because this will complete its outer shell with 1 S2 shell, and so therefore 2 is actually a complete outer shell. Lithium will also be happy to just have a 1s2 filled outer shell. Beryllium will happily just have 4 electrons in the outer shell, so actually half an octet, just like in BeF2. Another common reduced octet violator is boron, which has 3 electrons in the outer shell to begin with, and will also be quite complacent with just 3 bonds or 6 electrons in the outer shell, just like in BF3 or BH3, and boron is actually a really common one that's used in questions in exams, so watch out for that one. Aluminium, in the same group obviously as boron, can also form these reduced 6 electron outer shell. Now, AlCl3 is an example of this, although it would actually exist in the dimer form, not as I'm drawing it here, just to illustrate that there would be 3 bonds to that central aluminium. The other type of exception is, of course, an expanded octet, and these are atoms which readily form compounds that have more than 8 electrons to the central atom. Main culprits here are the 3p section of the periodic table. That's from silicon, phosphorus, sulfur, and chlorine. And the reason for the ability of these atoms to form an expanded octet is because there is the low energy 3d orbital, which is very near the 3p orbital in energy, and so extra electrons can kind of be shuffled up into that orbital, and so you can have something that has more than 8 electrons and still be stable. SO3 is an example of this, in which we have sulfur in the center bonded to 3 oxygen atoms, to which each it has a double bond, giving us a total of 12 electrons seen by that central sulfur atom. We'll actually deal with this in a little bit more detail when we look at formal charge. Now, the period 2 elements cannot do this because they don't have that 3d orbital, or even, and there's no such thing as the 2d orbital, just above for them to put those extra electrons in. So what we end up with then is something a little bit more like the octet rule of thumb than a rule. Now, this sharing can sometimes be completely equal between 2 elements. However, electronegativity, that's the relative attraction of an atom of an element to a shared pair of electrons, dictates how much the electrons lie towards one nuclei or the other. You can look at these values at Taper 8 in the data booklet. For example, if we have fluorine and fluorine, the electron cloud is going to be shared equally over both nuclei, as they both have the same value for electronegativity. However, if we look at HF and we look at Table 8, we see that fluorine has a much higher value of electronegativity, and so therefore the electrons lie much closer to the fluorine atom, and this gives us an unbalanced electron cloud which lies towards the fluorine. This is what we call a polar covalent bond, and we represent this using the lowercase Greek letter for delta, which indicates that there is a partial negative or partial positive charge. And because in this molecule that partial charge is unbalanced, we end up with an overall dipole moment. That means that this molecule in general has the electrons shifting to one side, giving us a dipole. Dipole just meaning 2 sides, so we have a positive and a negative side. So we have polar bonds caused by a large difference in electronegativity, and non-polar covalent bonds, which are caused when there is similar or the same electronegativity. Now, you don't have to remember these values, and you can also use Table 29 in the data booklet to actually be able to calculate whether you're going to have a polar or non-polar covalent bond. You can use the average electronegativity and the difference in the electronegativity to identify which type of bonding you would have based on this table. For example, if you had an average of 2.5 and a difference of 1, draw 2 lines across or use a ruler, and you'll see that they cross over right in the middle of polar covalent, so that bond would be polar covalent. We can have a look at an example. Let's say CO2. What type of bonding would we expect in CO2? Well, we can use our 2 tables. We look at the electronegativity of carbon and oxygen, which is 2.6 and 3.4 respectively. And then we take the average of those 2 values, which is 2.6 plus 3.4 over 2, which equals 3.0. And we want the difference between them, which is 3.4. Take away 2.6, which is 0.8. We can then use the Table 29 to find the type of bonding using those 2 values. Now, there is also the kind of side note that in general, differences between 0.5 and 1.8 are usually polar covalent, which is what we see here from the graph, the crossover point being just inside the polar covalent area. Looking at another example of CH4, we look for carbon and hydrogen, that's 2.6 and 2.2. We take an average, which is going to be 2.4. Then we find the difference, which is 2.6 minus 2.2, which is 0.4. And then we use those values on the chart just as we did before. And now we can see that we have a non-polar covalent bond, which we may have guessed by the very small difference in electronegativity. So going on from what we mentioned on the last slide, any difference between 0 and 0.5 is usually non-polar covalent bonds. Just as anything above 1.8 is usually an ionic bond, which we'll come to later in the unit. Let's try some questions. Having the data book with you is going to be helpful here. First question, determine the nature of bonding you'd expect between carbon and oxygen. Pause the video, give yourself a moment. Bop, boom, bop. So once again, finding the average and the distance by using table 8, 2.6 and 3.4 gives us an average of 3 and a difference of 0.8, which is going to be a polar covalent bond. Okay, have a go at doing the same, but with lithium and oxygen this time. Pause the video. Pop 'em up. So lithium having electronegativity of 1.0 and oxygen being 3.4, we take the average, 3.4 plus 1 over 2 is 2.2, and the difference is 3.4 minus 1, which is 2.4. That is going to be an ionic bond. Looking beyond the individual bonds now, we can look at how the organization of covalent structures can occur. This happens in two groups. We have simple covalent compounds and giant or macromolecular covalent structures. Simple can be broken down into polar and non-polar simple covalent compounds. So let's have a look at the physical properties of these kind of structures. Firstly, they do not conduct electricity. Now, the solubility will depend on whether they are in an organic or inorganic solvent and their structure relating to that. Their boiling point is generally low because they're not extended molecules, and the only thing that is holding them together are weak intermolecular forces, which are easy to break. We'll have a look at those more in detail later in the unit. So they don't conduct electricity for the same reason. There's no way to carry charge throughout the compound because they are separate molecules, and that means that it's easy to separate the molecules, so they're likely to be gases or liquids at room temperature. In fact, I2, which is iodine, is one of the only simple covalent structures that is a solid at room temperature, and that's mainly to do with the intermolecular forces, again, which we'll cover later in the unit, and it sublimates, which is also to do with these intermolecular forces, that when they are overcome, we go straight from a solid to a gas. It's actually quite a beautiful purple gas. So giant covalent structures such as diamond, graphite, silica, etc. These differ slightly in that they don't have individual discrete molecules. Instead, we have these extended lattice structures which have covalent bonds that go on and on, forming a kind of infinite covalent lattice in which every single bond is a covalent bond. Being very strong, that means that all of these bonds require lots of energy to break them, which gives us a different set of properties. Now, they still don't conduct electricity because there's no way for them to pass electrons or charge through the molecules, except in the case of graphite, which we'll look at. They have very high melting and boiling points, again, because if we want to melt or boil these, we have to break every single carbon bond. And they also are very hard, again, apart from graphite, because of the very strong covalent bonds in that lattice arrangement. So the next covalent structure we're going to have a look at is silica. And silica actually resembles the diamond structure in many ways because it has this tetrahedron-like shape, except now we have both carbon and oxygen atoms composing the overall lattice structure, but still all bonded by these individual, very strong covalent bonds. But now we have oxygen atoms in between each of the silicon atoms. So this is kind of one repeating unit, if you like, and then we would have the same kind of tetrahedral continuation further along the lattice structure as we had with diamond, but with the oxygen and silicon repeating. Now, with the empirical formula SiO2, sometimes you can look at this overall repeating structure that I've drawn here and think, well, that looks like it's a one-to-one relationship between silicon and oxygen. However, if we look a little more closely, what we see, if we think of the black as the silicon and the orange as the oxygen, every silicon is bonded to 4 other oxygen, and every oxygen is bonded to 2 other silicon, and hence we have the ratio SiO2, a 2-to-1 relationship. Silicon dioxide, of course, being the major component of sand and many rocks, and this has similar properties to diamond, i.e. a very high melting point and boiling point, and they're very strong, and that again comes from this infinite tetrahedral lattice that is formed from the silicon and oxygen bonds. Now, because there's no mobile electrons or ions, there is no electrical conductivity through silica, just like in diamond. Now, as I mentioned diamond, I've already alluded to the fact that there are different forms that carbon can take, and these forms are called allotropes. So an allotrope is where there's 2 or more different forms which an element can exist. So for carbon, this is diamond, graphite, charcoal, Buckminster fullerenes. We also have things like graphene and carbon nanotubes. But basically they're all carbon, and the only difference between them is the way in which the atoms are bonded together and the structure that they form. This means we have an incredibly high melting point. In fact, carbon doesn't have a boiling point because it sublimates at over 4,000 degrees centigrade. That means going straight from solid to gas. It's very strong and very hard, indeed the hardest substance that humans know of. And there's no free electrons, and so it is not an electronic conductor. Now, graphite is another carbon allotrope, so still made completely of carbon. However, the structure is very different, and this structure leads to a couple of significantly different properties than we would expect compared to that of diamond. We basically form these 6 carbon rings, which are bonded in an extended lattice, as I've shown here. And instead of having 4 bonds between each carbon, we have 3 bonds between each carbon, and then those layers are on top of each other. So that extra electron that carbon has, instead of forming that 4th bond, kind of gets delocalized between the 2 layers. So it still has a very high melting point and sublimates just like that of diamond. However, this delocalized layer of electrons causes it to be soft, and that's why graphite is used in the lead of pencils, because it is easy to smear effectively that layer of graphite onto the page, which is what we associate with a pencil mark. That is because in between these 2 layers, we only have weak intermolecular forces. We don't have those strong covalent bonds that we see along those 3 other bonds between the carbon atoms. We have these interactions, and those interactions are much easier to break and require much less energy, allowing the layers to easily slide over each other. The other thing that these delocalized electrons allow is they allow the conduction of an electrical current through the substance, hence why graphite is a good electrical conductor. Now, if we take just one of these layers of graphite, we end up with graphene, which quite simply is just one layer of graphite, but changing some properties, interestingly raising the melting point even further to sublimation above 5,000 degrees. It's also the strongest material that's ever been tested. It's transparent and it conducts electricity extremely well, and has in many applications been touted as a potential super material for some applications. And carbon doesn't stop there. Indeed, fullerenes, or Buckminster fullerenes, that were first theorized before they were discovered, are these kind of football shaped, where we have 5 rings and 6 carbon rings all joined together to form this large sphere, have a reasonably high melting point of 600 degrees, but these are individual discrete molecules, so they don't exist in the same way as that long extended lattice structure of the other allotropes of carbon. And this makes them quite soft because these individual molecules are only held together by weak intermolecular forces, and so these individual ball-shaped molecules can slide over each other quite easily. For the same reason, it does not conduct electricity because there's no free electrons. However, it does have a really important property, which that it can kind of be opened and formed into these carbon nanotubes, which again also have been touted as an important potential future material. Before we finish up then, let's get our whiteboards ready and try some questions. Firstly, explain using the structure of the allotropes why graphite can conduct electricity but diamond cannot. Pause the video to have a go at that. Pop 'em up! So hopefully remembering that graphite has free moving electrons between its layers, which allow it to carry charge. Next question, why does silica have a higher melting point than iodine? Pause the video to have a go at that. Pop 'em up! So of course, silica having a giant covalent structure and iodine only having a molecular or simple covalent structure, and so therefore requiring much less energy to overcome those intermolecular forces. Okay guys, no practical to go with this and no questions just yet, as we're going to do Lewis structures in the next video, and then we'll try and apply our knowledge to some problems. Thanks again for joining me guys. Don't forget to like, subscribe, hit the bell icon, you know the drill. As always, practice makes slightly better.